It's my pleasure to introduce or invite Datar from the Indian Institute of Science to give the talk this afternoon. He's going to talk about J stability and the J equation.
Yeah.
That's briefly the tech. Okay.
I decided to modify the title because there will be very less of stability in the talk. But yeah, thanks for the introduction and thanks for the invitation to the organizers. So I'm going to talk a bit about some recent work on the J equation due to myself and some collaborators and several other people. So I thought I'll just sort of give a broad overview of this area. So here's the outline for the talk. So I'll first give a little bit of background on the J equation, why people care about it. And I'll end this section by mentioning the analog of the Hitchin-Kobayashi correspondence for the J equation. Then I'll maybe describe a relatively new program to construct canonical weak solutions to the J equation. And then in the last part, I'll describe some sort of quote-unquote new results. So these are about a couple of years old, but I was hoping to add to that before this talk, but I haven't got around to doing that. So this will basically be a description of some results that I've already talked about in the past. Unfortunately, so those of you who have listened to my previous talks on the topic can doze off without losing anything. So yeah, let me maybe just give you some background on the J equation. So the setup will be as follows. So X omega is always going to be a compact scalar manifold. And N is going to be the dimension of X. Omega being a scalar metric, it represents a cohomology class, which I'll denote by beta. So beta is the class of omega which lives in sort of the intersection of the second de Rham cohomology and the 1-1 Dolbeau cohomology. And alpha is going to be another scalar class. So I'll denote by kx the scalar cone of the manifold X. So this is basically the space of positive classes in H11. So for instance, I mean, obviously beta also belongs to kx. And I'm going to fix a reference form. So I fix a reference form chi in alpha. So this is going to be a reference positive closed 1-1 form. Okay, so then by the sort of classical DD bar lemma, if you look at all other representatives in this class, they basically differ they're parameterized by smooth functions. So I'm going to use this notation throughout. This is going to be chi plus I DD bar of phi, where phi is some real valued function. And often this is also going to be a positive form, right? So phi is going to be a quasi PSH function. Right, so the J equation basically seeks a function phi which solves the following PDE. So you take the trace of this fixed background scalar metric with respect to chi phi, that ought to be a constant. So that constant is usually denoted by mu. Okay. Now, just by the definition of what this trace means, this is basically n times chi phi to the n minus 1 wedge omega divided by chi phi to the n. So if you multiply out if you clear the denominator and integrate on both sides, this implies that mu, this topological constant, is basically just given by an intersection number. Okay. Right, so this is sort of the analog of slope in the whole vector bundle story. Right, so why would you bother with this equation? So here's some motivation to, why were people interested in considering this equation in the first place? So I believe the first person to write down this equation was probably Donaldson. So he has this paper on moment maps and diffeomorphisms where he sort of writes down a moment map which leads directly to, like all sort of interesting PDEs and complex geometry. This also has a moment map origin story that is due to Donaldson in this case. But I won't elaborate on this, partly because I don't remember the details and it's irrelevant for the talk. The second sort of big motivation was due to a formula that Shushong Chen wrote down. So that basically related the solvability of the J equation to the more sort of famous CSCK problem. Especially for manifolds whose first Chern class is negative. So the idea here was that there's a classical functional called the Mabuchi functional, which is known to, the critical points of the Mabuchi functional are known to be CSCK metrics. So Chen discovered this formula that the Mabuchi functional can be decomposed into something called as the entropy functional plus something which traditionally has been called the J functional. And it turns out that the entropy functional, so variationally, if you want to find critical points, it turns out that the Mabuchi functional is convex on the right space of geodesics and so on, geodesics in the space of Kähler metrics. So in order to find critical points, one ideally would like to sort of minimize this functional, in which case, it helps to know whether the Mabuchi functional is proper or not. It turns out that this entropy part is always proper. So as long as you know that the sort of J part is bounded below, the combined thing will be proper. And then one could actually find sort of CSCK metrics on manifolds with negative first Chern class. Why does negative first Chern class matter? It's because in that case, one can actually choose a reference form chi so that omega can be taken to be minus Ricci of chi. And then it turns out that this functional actually is also well behaved. It has nice convexity properties. So now one can sort of just abstract away from this problem and just look at the J functional by itself. And instead of minus Ricci of chi, one can just replace some other background form. And that leads you, the critical points of that are precisely solutions to the J equation, right? So that was one important motivation for Kähler geometers to care about the J equation. Right, so there are a few other sort of motivations. Another important motivation is that one can look at sort of general complex Hessian problems. So, so these are basically, you let lambda 1 up to lambda n be eigenvalues of this endomorphism. And you can just look at the PD that's given by, where this is some known function. Right, and f is a nice sort of convex function on some subset in Rn. Okay, so such problems again have a rich history. They've been considered even by Riemannian geometers. These sorts of PDs also make sense on Riemannian manifolds and so on. So the J equation in some sense is the sort of simplest case of a complex Hessian equation that's not the Monchampier equation. So if you take, for instance, just to give you an example, if you take f to be summation of logs, then the corresponding equation will, after exponentiating, will just be the Monchampier equation where you're prescribing the product of the lambda i's. Right, so apart from the Monge-Ampere equation, if I'm to write down the simplest sort of complex Hessian equation, that would be the J equation. So that's another motivation to study the J equation. Right, so maybe before I tell you the optimal sort of the Kobayashi-Hitchin correspondence for this equation, let me maybe write out a special case. So let's look at the case n equals 2. Right, so here if you look at the equation, that's just chi squared minus 2 chi wedge omega is 0. So one can do what we learn in high school and just try to complete squares. So if you complete squares, this is equivalent to the equation chi phi minus 1 by mu times omega squared is this, right? So this, of course, looks like the complex Monge-Ampere equation, and in fact, by Yau's famous resolution of the Calabi conjecture, this has a solution if so it has a solution with chi phi minus 1 by mu omega positive if this class alpha minus, so chi phi belongs to the class alpha minus 1 by mu beta is actually a Kähler class, right? And then of course, to decide whether some class is scalar or not is in general a difficult problem because it involves a pointwise condition. You have to actually come up with a form such that some form minus 1 by mu times omega is positive. That's in general a hard problem. So what one does is try to replace this with some numerical condition where you just compute some numbers and check whether they're positive or not. So this is done via the classical Nakai criteria, which was extended to, in the transcendental case, by Demai and Pon. So what this says is that all you need to do is to check that for all curves, the integral of alpha on the curve multiplied by mu is bigger than the integral of beta on the curve, right? So, so you just replace, I mean, this condition is much easier to check than this pointwise condition, right? So that's going to be the theme of this lecture today, that we'll see shortly that solving this equation is actually a necessary condition is checking that a certain pointwise condition holds. And then the whole sort of game is to replace that pointwise condition with some numerical condition so that you can just check the positivity of some numbers, okay? Right, so let me go back to the sort of general equation and let's talk about some necessary condition. Right, so I can do something silly. So if you look at the way, I mean, why is the J equation, so maybe I'll write it here. In the case of the J equation, if you want to write it as a complex Hessian equation, that's simply given by summation, the reciprocals of lambda is, they add up to mu, because this is exactly the trace of omega with respect to chi phi, right? So the J equation is precisely given by this. Okay, so I can do something silly for any j because my lambda i's here are positive. So I can do something silly. I can just drop one of the lambda i's, and then you ought to get a strict inequality, right? So that's clearly a necessary condition. So necessary condition is that for all, let's say j from 1 to n, summation I not equal to j of 1 by lambda I is strictly less than, right? So somewhat helpfully, there is actually a more sort of intrinsic way of writing this. This turns out to be equivalent to the statement that mu times that there exists a chi such that mu times chi to the n minus 1 is bigger than n minus 1 times chi to the n minus 2 wedge omega. So as an inequality of n minus 1 and minus 1 forms. Right, so a necessary condition is clearly that you must have this inequality. You must have at least one chi in the class so that you have this inequality. And in fact, you can, I mean, why stop at just dropping one? You can drop p of them. If you drop p of them, it turns out that this is actually equivalent to, or maybe m of them. This is actually equivalent to this condition. Okay, so I want you to think of this more as an analog of the Kähler condition. In the Kähler condition, in the complex Monge-Ampere, we wanted some form to be positive. Here you just have these n-1 positivity conditions, pointwise again, right? So they're at least necessary conditions. And then it was proved by Song and Weinko, in I think 2012, that I'll write this as the cone condition, C. So C actually implies existence of solutions to the J equation. Okay, so this is a purely PDE result that assuming the positivity of some forms, you actually get existence of solutions to a PDE, right? So that's a purely PDE result. There was then a conjecture due to Lejmi and Zeklihidi that in fact, if you look at these sort of pointwise conditions, if you integrate that on an m-dimensional, let's say, analytic set inside your X, then of course the necessary condition is that you have to have the inequality for some intersection numbers. So they conjectured that in fact, if for all purely m-dimensional subvarieties or analytic sets, if you have this inequality, so think of this as the definition of the slope of Z. So that's just the dimension of Z times the quotient of some intersection numbers. So this should be M. If this is smaller than mu, then your topological constant, then you have solution. So this is what they conjectured, and this is clearly necessary just by integrating both sides, right? So it turns out that their conjecture is actually true. So let me state the optimal sort of result on existence. So this is mainly through the work of Gauchen, who proved a sort of uniform version of this, where you replace mu by 1 minus epsilon times mu. If that condition holds, then he showed existence of solutions. And then this was improved by, in the projective case, by myself and a colleague, Vamsi, who's, I suppose, spoke about something else last week. And in the general Kähler case, this was proved by Song. Right, so the optimal result, you can think of this as the analog of the Hitchin-Kobayashi correspondence, is that suppose for all Z, you have this inequality of the slopes. So you can think of mu as the slope of X itself. Then this is actually equivalent to the J equation having a solution. Okay, has a smooth solution. All right, so once that was done, a natural question to ask is what happens in case you don't have these inequalities. So what happens in the unstable case? So let me maybe make a definition. So we say that X alpha is J slope stable if this inequality holds for all Z. So if for all Z in X, mu of Z is strictly less than mu of X. And correspondingly, we have notions of semi-stability if you allow equality, and unstable if not semi-stable. So what this statement really says is that the J equation admits a smooth solution as long as you're in the slope stable regime, right? So exactly the sort of analog of the Hitchin-Kobayashi correspondence. Right, so So people who are familiar with the CSC case story will know that in the whole area of case stability, there's another sort of how do you check stability? You basically allow these things called as test configurations, and then you have a certain weight called the Futaki invariant. You test the positivity of that. So there is actually a corresponding story for even the J equation. This was developed in the paper by Lejmi and Zeklihidi. And it turns out that, in fact, J stability defined that way is actually not equivalent to J slope stability. So J slope stability is actually equivalent to existence of smooth solutions, but it turns out that J stability defined in the Lejmi-Zeklidi way only gives you J slope semi-stability. So you don't get full J stability. So this was due to some relatively recent work of Hattori. Right, so why would one, so as I was saying, I mean, the question is what would happen in the unstable case or even the semi-stable case? So again, motivated by the vector bundle picture, one would expect that there's some sort of decomposition happening into sub-objects that are at least semi-stable. But all that is, at least for the J equation, all that is sort of conjectural. Our motivation was actually to look at some other problems. So the first motivation was from something called as the J flow, which is the parabolic analog of the J equation. So J flow was again, I think, studied for the first time by Shushong Chen. And he showed that, so this flow is basically just given by, it's at the level of the potentials, it's simply given by this. You start off at some P naught. All that you know about this phi naught is that chi phi naught is a positive, is a Kähler metric. So what Chen showed is that this flow actually lasts for all time. So then it makes sense to ask for the long time limit of this flow. And so natural question is, what is a long time limit of this? So our feeling was, and I'll describe an example in a moment, our feeling was that the long time limit should also satisfy some sort of J equation in the weak sense. Right? So our whole sort of our main motivation was to understand what sort of equation these limiting metrics to the J flow should satisfy. And the second motivation is basically minimizers. It comes from the famous Atiyah-Bott formula. So in the context of the J equation, this would be something that looks like you take the infimum of, there's a corresponding L2 energy to the J equation, which is called the Donaldson L2 energy. So that's simply given by this. You take the infimum of this. This should somehow, I mean, this infimum is clearly positive in the case that there's no solution to the J equation. So this should tell you something about the maximally destabilizing subvarieties. So the conjecture is that this should be equal to the supremum of minus of the relevant Donaldson-Futaki invariant, where you take test configurations for this class, X and alpha. Right, so one side of the identity, so namely that this infimum is bigger than the supremum actually holds. This was proved in the case when alpha and beta are integral classes in the original work of Lejmi and Zeklidi, and I suppose the extension to the transcendental case is more due to Rui Dervan and probably Julius Ross and their combined work. So you do have one inequality, but you would expect that there's an identity of this sort that should hold. And then an expectation is that a minimizer somehow, I mean, your minimizing metric should somehow capture the maximally destabilizing subvarieties in some way. And that should be, analytically, that should be through some weak solutions to the J equation in the unstable case. So that's the conjectural picture. So let me maybe be a bit more precise. Yeah, I guess before that, let me describe an example. So you can take the simplest possible example, namely that of the blow-up of P2 at a point. So one can think of this as a ruled surface. So this is just projectivization of O plus O minus over Pn minus 1. So just to draw a picture, there are these two divisors, namely the exceptional and the hyperplane divisor, and this can be thought of as a projective bundle over the exceptional divisor, which is a copy of Pn minus 1. And it turns out that just by rescaling, one can assume that alpha is of the form A times H minus E, where A is bigger than 1 because we want alpha to be scalar, and beta is given by this. And then there's this well-known method in scalar geometry called the Calabi-Ansatz, that you assume that your metrics only depend on the sort of fiber distance from the exceptional divisor. So you assume that chi is given by del bar of u of rho, where rho is log mod s squared, where mod s squared is roughly like the fiber distance from the exceptional divisor. And you assume that omega is also of this form, where both u and v are strictly convex real valued functions. And then it turns out that the J equation has a particularly simple form. So because these two are convex, u prime is a strictly increasing function from R to the interval 1 to A, and v prime is a strictly increasing function from the interval from R to 1 to B. So one can consider psi, which is given by v prime composed with u prime inverse. So that's a map that goes from goes between these two intervals, and then one can write down what the J equation is. Remember that V is sort of a fixed potential. We are essentially solving for U. So solving for U is equivalent to solving for an appropriate psi. And then for psi, the equation reduces to a nice integrable ODE. I think this is either n mu or mu, probably mu. Right, so I mean, obviously by just using an integrating factor, one can completely solve this. But the key is that one wants psi to be strictly increasing. So one can check that this is equivalent to the condition where mu is either bigger than 1, n or bigger than 1. I forget what the correct normalization is, but in one of the regimes, you know that you can solve for a strictly increasing psi. And lo and behold, this turns out to be exactly the stability regime. So if mu is bigger than n or bigger than 1, this pair x alpha is going to be stable with respect to beta in this case, right? So natural question is, with Calabi symmetry, one can study the J flow and get a whole family of these functions psi which now depend on time. What is the limit of this? It turns out that the limit is given by the following. So this was done by Haofang and Ma. It's basically constant 1 on the interval 1 to lambda, and then it converges to some sort of limiting function on the rest of the interval, where this lambda is equal to 1 if and only if this is semi-stable. So in the stable case, there is actually a jump that it converges to something that's constant on some non-trivial interval, and then it converges to some function. And psi infinity solves a J equation of the form psi infinity tilde prime plus n minus 1 by x psi infinity tilde is some sigma, where sigma turns out to be strictly lesser than mu. So it does, the limiting thing actually does solve a sort of J equation with a slope that's reduced, right? So this was one of our sort of main motivating examples. So what we were able to sort of interpret, we were able to interpret this result in the language that we were interested in. So in fact, these were the observations that we started off with. So this is due to some collaboration with my student and my former advisor, so 3 generations of us. So this says that the sigma is actually given by the infimum over the slopes computed for these perturbed scalar classes. So where alpha s is the original alpha minus you take away a little bit of the exceptional divisor. Okay, and such that when you perturb your Kähler class, you land up in the semi-stable regime. Okay, so that was our first observation, that there is a nice sort of geometric characterization of this sigma. And similarly, there's also a nice geometric characterization of lambda. So this is the infimum of S such that this pair is semi-stable. Okay. So essentially, if you're in the unstable regime, you just pull out a little bit of the exceptional divisor, you land up in the stable or the semi-stable regime, and then you compute the slope and take the sort of minimal slope possible, and that turns out to be the right slope, at least for this example. So that led us to the following definition of what we call the minimal slope. So we define this to be the infimum of all these slopes where now instead of working with just x, you work with birational models of x. So this is a modification. D is an effective R divisor. Alpha tilde is a perturbation of alpha by D, right? Such that this pair is stable with respect to, or semi-stable with respect to the pullback of beta. So I realize that the pullback of beta is not really Kähler, but you can define all these stability notions even allowing beta to not be Kähler. Right, so then we have a series of conjectures that we are able to verify in some examples. No, so D is just some effective divisor such that this pair is semi-stable. So choosing D is part of the data here. So this is sort of infimum over all modifications and D. So you choose, so it turns out that for the blow up, all the divisors that you need to test against are basically just multiples of the exceptional divisor. And similarly for, we actually also talk about more general projective bundles where again you sort of just take the blow up along the 0 section and subtract out the exceptional divisor of that, and that's enough. Right, but in general, we don't know what kind of divisors will show up, except in one special case. Right, so let me maybe just sort of list down the conjectures. So the first conjecture is that there exists a unique current which solves the J equation with mu replaced by this new slope. And because this is a current, you in general cannot take wedge products of currents. So Bedford and Taylor have this very classical theory where you can take wedge products of these currents as long as they're bounded local potentials. Here, one would expect that they don't have bounded local potential. So instead of the Bedford-Taylor wedge product, we have to take what is called as a non-pluripolar product, also introduced by Bedford and Taylor. So to replace the wedge product with this more general sort of product, and this ought to be equal to this. Okay. So, so I don't want to go into the technicalities of what this actually is. Maybe I'll just say a sentence on this, that suppose T actually has bounded local potentials outside of some pluripolar set or say some subvariety, then this is basically just like taking the Monge-Ampere product outside that subvariety and extending it by 0 across the subvariety. So in general, this is going to be a measure, and similarly on the right. So we have a conjecture that you should be able to solve the J equation, but with the mu replaced by this new slope. The second conjecture is about the J flow. So if this is a solution to the J flow, then we expect that the corresponding currents converge weakly to T. So already by this general Harnack principle, if you take away the supremum of phi T, then you'll have some L1 convergence. So our expectation is that if you take chi plus dd bar of that L1 limit, that should be this singular solution to the J equation. And the third conjecture is about the Donaldson functional. So we conjecture that there exists a minimizing sequence in this class. So the limit as A approaches infinity of the Donaldson energy along this sequence is precisely the infimum. Then we expect that these chi k's, or at least after passing to a subsequent, should converge weakly to the singular solution that we are constructing, or we are conjecturing. No, so I think one would, at least for surfaces, we know that this is sort of given by essentially the negative part of some Zariski decomposition, but in general, I have no idea, other than for basic examples with symmetry. Right, so in general, I mean, one hopes that this actually captures all the subvarieties where this slope condition fails. But yeah, as we are discussing in the morning, there will be some multiplicities, and at the moment, even for surfaces, I don't really know what that means, but yeah. Right, so so maybe let me, before I wrap up, let me quickly give you a brief digression on the complex Monge-Ampere equation. So, so of course, our definition of this was motivated in part by this observation with the sort of simple blow-up examples. But there was another motivation that comes from the complex Monge-Ampere equation. So the big theorem here is, of course, Yau's theorem, and then one can sort of adjoin the Nakai criteria generalized by Demai and Pon to the transcendental case, which says that so one looks at maybe a class H11R, and one looks at a volume form. Then basically this equation has a solution. So chi to the n is c times omega for some positive chi, if and only if alpha is scalar. This was, of course, the big theorem of Yau. One direction is obvious, because if you're assuming that there exists a chi positive, that by definition implies that alpha is a Kähler class. So the hard part is that's really a PD result as the opposite direction, that if you take a Kähler class, then you can actually solve this this PDE. And if you adjoin this sort of Nakai criteria, which is saying was generalized to the transcendental case by Dimai and Pon, what this means is that for all subvarieties or analytic subsets of pure dimension M, if you take, and let's say for all k from 1 up to M, if you take something like this, this should be positive, right? So actually in the projective case, you can even drop this. So just this intersection number should be positive. But in the non-projective case, say on generic complex torus, you also need this additional term. Right, so natural question to ask is what if alpha is not in the Kähler cone? Do you actually still have a solution? And this was answered by 4 people, Buxom, Esidiu, Gedge, and Zeriahi. So this is their sort of big theorem in 2010 or something. So this says that suppose omega is a sort of sufficiently nice probability measure, then in fact there, I should say that this constant here is precisely given by alpha to the n by the total volume of X with respect to omega, right? Just integrate both sides. So this is of course a necessary condition, but Yao says that this is actually sufficient as long as alpha is scalar. Right, so what BGZ did is that if omega is sufficiently nice, which just means that it doesn't charge a class of sets called as pluripolar sets, then in fact one can solve an equation of the following type. So there exists a unique current T in alpha, so that this is equal to C times omega, where C this time is given by an invariant called the volume of alpha. So I should say that suppose alpha is big, right? So it still needs some sort of positivity, namely that it needs to have at least some nice enough positive current in its class, but it need not be Kähler. This is much weaker than being Kähler. What BGZ says is that you still can find Kähler currents in alpha which solve this Monge-Ampere equation. And in fact, this invariant volume, this is a generalization of the notion of volume of big line bundles from algebraic geometry. This has a characterization that looks very similar to that. So this is basically just the infimum of over again pi and b. Where again you take a modification, you take a divisor, effective divisor, such that pi star alpha minus d is big NF. Okay. So there's this characterization of the volume functional, and that was essentially a motivation for us to consider things of this sort, that and that it works in the case of this special example. Right, so maybe I'll end with stating our main results. So, so this is a theorem obtained jointly with Ramesh Mete, who should be somewhere in the audience, and Jian Song. So what we show is that firstly, conjecture A holds on complex surfaces. So we are basically able to reduce, again, by completing squares, we are able to reduce the J equation to some sort of a Monge-Ampere equation in the style of BEGZ. The only sort of hard part is how to get to this value of sigma. So we need to show that we can actually solve with the appropriate value of sigma. And that basically comes down to the fact that there is a Zariski decomposition in the case of surfaces. So the reason why we need sort of modification, and even for the volume functional, why you need modifications is that there's no sort of notion of Zariski decomposition in higher dimensions. You can only get things up to modified Kähler classes, or modified Neff classes, not really Neff classes. So, so our first main result is that conjecture A holds on complex surfaces. So it turns out that the proof of this is actually quite elementary. It's just playing around with Zariski decompositions. But I would say that at least the idea was quite novel, because I don't think writing down weak solutions was really done, besides, for the complex Monge-Ampere equation, which of course has a lot of theory behind it. But for other complex Hessian equations, I think this seems like the first such attempt. But on the other hand, the actual proofs are quite elementary, because you're just dealing with surfaces and just play around with some Zariski decompositions. On the other hand, we also are able to show that conjecture A to C actually holds for some projective bundles. So we consider projective bundles of the type, this is sort of just a generalization of the blow up of P2 example. Where L is some negative line bundle. So here, actually, the proof is quite technical, but the main ideas were already there in Haufang and Ma's work. The only problem was there were some claims made in those papers that we didn't quite understand, and so we had to work a bit hard to try to elaborate on those. So this is sort of the technical heart of our paper, but the ideas here were not really that new. Only the interpretation in terms of these minimal slopes, etc., was a bit new. But on the other hand, the basic idea was already there in Haufang's work. Right. So these are our two sort of main theorems, and maybe I'm almost out of time, so maybe I'll end here. Yeah. Thanks.
Comments?
I just wonder about the J-flow part B. Is there some way in dimension 2 of rewriting the J-flow as something related to a Monge-Ampere flow?
No, I don't know. I've tried that, but it doesn't seem obvious at all. Because, I mean, part of the problem is also that if you want to write something in terms of the Monge-Ampere flow, you have to sort of assume that this perturbed class is already Kähler, whereas in our case, in the case of the J-flow, you don't actually know that until the limit, right? So for instance, the J-flow can actually be started with any sort of chi-naught which is positive, but chi-naught may not, even in the smooth case, when you expect smooth solutions to exist in the stable case, chi-naught does not satisfy this inequality, right? But the limiting thing does. So if you want to really relate it to the Monge-Ampere, so I've actually written down the J functional, and if you account for this perturbed class, the J functional is actually exactly equivalent to this E functional that shows up in Buxom, Berman, etc., right? So there must be a relation, but there is this loss of positivity. You don't, when you start the J flow, you don't really know whether chi-naught is bigger than omega by mu. Right?
But if you're content to run some kind of pluripotential theoretic Monge-Ampere flow?
Maybe, but I thought that all of these functionals needed some sort of positivity to, even for the convexity arguments, etc. to work. Right?
You just need some kind of big hypothesis rather than a Kähler hypothesis, I think.
I see.
But I'm not sure that really helps, but at least I'm not sure that.
I see. Yeah, so maybe then, yeah.
Thanks.
Can you comment on the relation of the J equation with the deformed Hermitian-Yang-Mills that we have heard here?
Right, so yeah, that's a good point. I should have mentioned that, so I think this, I don't know this story that well. I think Rui probably knows this better, but if you look at the Z-critical equations that he talked about last week, then I think in the large volume regime, for the special case of line bundles, these are sort of the deformed Hermitian-Yang-Mills. Did I get that right? And the small volume limit is the J equation, or? Oh, I see. Okay. So, but I mean, if you write down the deformed Hermitian-Young-Mills, there is a way to sort of scale, and in some scaling limit, this actually does give you the J equation. So, so I would say that this is sort of the simplest test case. I eventually do want to, so we actually have analogous results also for deformed Hermitian-Young-Mills, but they're a bit more complicated, partly because you have much less positivity for the deformed Hermitian-Young-Mills. So for instance, I mean, we have a conjecture in our paper, but I'm not even sure whether that's the right conjecture. But our eventual aim is to really get to the deformed Hermitian-Young-Mills. And I think the J equation is sort of the simplest model to study in some sense. So for instance, I mean, even this conjecture on minimizing Donaldson's energy. So I have some very vague ideas about how to do this for the J equation. And ideally, I would like to extend this sort of thing to deformed Hermitian-Young-Mills, because there you also have this major open problem on how the deformed Hermitian-Young-Mills stability is related to Bridgeland stability conditions. And hope is that this sort of analysis might shed some light on that. But I'm not an expert in this area. But
no further questions. Let's thank the speaker again.
Thank you.